Morning. Okay, so today we're going to finish, well, not finish, but just say a few extra words about what we finished with last time, which was the derivative of a map between manifolds. And then we're going to go back finally, after a long trip away, back to some physics, and we're going to talk about rigid body velocities, okay? So last time, remember, we defined TF. So if we had F from M to N, then we define TF from TM to Tn. And the definition was that it took a tangent vector at M, tangent vector on M at X, which is by definition of a tangent vector an equivalence class of curves, and then it maps it to a tangent vector on N, which is also an equivalence class of curves, and it's this curve whose equivalence class you take. Okay, and we talked about this last time. We talked about what sort of drew a cartoon attached to this, and we gave the local representatives for these things last time. Okay, and we saw that the local representative in the kind of vector part for the tangent bundles in coordinates was just the ordinary Jacobian derivative of the local representative of F. Okay. So now what we want to do is we want to look at two special cases. The first is for when F is a function, and so it's real valued. Okay. And so in this case, TF is a mapping from Tm to Tr. But we've seen previously, we established this explicitly, that the tangent bundle of any open subset of Euclidean space is, as a manifold, diffeomorphic to the open subset cross Rn. And so in this case, we're looking at open subsets of R, and the open subset of R is R. And so this is R cross R. Okay, and so this explicit representation here of the tangent bundle allows us to kind of do a more elementary form for TF in this case. So then TF. Okay, so we're going to evaluate TF on a tangent vector, and here I'm going to write a tangent vector at X. I'm not going to explicitly need the equivalence class of curves characterization of a tangent vector, so I'm just going to write a tangent vector at X like this. Okay, and so what's this going to look like? Well, first of all, it's going to be in here. Okay, so it's going to have two components. The first component is just going to be f of x, the value of the function, which is a real number. And then what am I going to get here? I'm going to get a linear, right? Because it's going to be a linear mapping from the tangent space to M at X into the tangent space at f of X of R. So in other words, what that means is it's going to be a linear mapping from the tangent space at X into R. And what's that? Well, that's just a cotangent vector, right? And what is that cotangent vector? Well, of course, it's the cotangent vector that we introduced last time, which is the differential of F. And so this is dfx acting on Vx. Okay, and so remember that this little angle bracket semicolon notation simply means that you're going to take this guy right here, which is a cotangent vector at X, and this guy right here, which is a tangent vector at X, and you're just going to take the cotangent vector and eat up the tangent vector to get you a number. Okay, so so it's a number. Okay, good. So that's one special example. And so what you see here is, so last time we gave an alternative definition of df, right? And so the way we defined df last time is we defined it in coordinates, okay? And then what we did was we showed that representation was independent of the coordinates that we chose, okay? Here we're doing it a different way. Here we're giving a definition of df directly without using coordinates, okay? And that's sort of a thing that you run across quite often, is that you have some object that you want to build in some way. You know, it comes from physics or mathematics or whatever kind of problem you're working on. And you have this kind of object that you want to define somehow. And first of all, you have to kind of figure out what kind of object it is. And so in this case, the object is that. And so it turns out that's a cotangent vector. So, you know, if you figured out what kind of object it is, then you can maybe think about how to define it in two separate ways. One would be with coordinates, and then show that your definition is independent of coordinates, which is how we did df last time. Or you can try for a direct definition independently of coordinates, okay? You know, when you grow up and become fancy, the second one becomes the way the cool kids do it. But when you're starting out, doing a coordinate definition and proving that it's independent of coordinates is almost always going to be the easiest way to go. And even as you get older and become more experienced, sometimes it's easiest to define things using coordinates. Okay. All right, so that's the derivative of a scalar valued function. Now we're kind of going to do the opposite thing. It's not going to be a function from m to r, it's going to be a function from r to m, which is a curve. And so we're going to have gamma from an interval I into m, okay? And so T gamma is going to be a mapping from Ti to Tm, okay? But remember the Ti, because again, let's take the interval I to be open, and then Ti is going to be, because I is an open subset of R, it's just going to be I cross R, okay? All right, so we're going to do kind of the same thing. We're going to use this simple characterization of Ti to come up with an explicit way of writing this thing down. Okay. So what does this thing look like then? So then T gamma is going to take a point in I cross R, and so a point in I cross R. So a point in I, well, you know, we think of gamma as certainly being a function of T. So the point in I, we're going to label it as T. And then there's kind of the vector part of Ti, and let's just call that A. It's just going to be some number. Okay. And so this thing is going to be, okay. So what will this be? Well, this is going to be Ti at, oops. T gamma, okay, is going to be, when I evaluate it at T, is going to be a linear map, which maps the scalar A into the tangent space at gamma of T of M. Okay, and so it's going to be a linear mapping essentially from R into M. Okay, and so a linear mapping into a vector space is simply going to be scalar multiplication by some vector. Okay, so the point is that there's going to be some vector A, V, and V for some vector V in T gamma of T M. Okay, so a linear mapping from R into a vector space is just scalar multiplication by some vector. Okay, and the vector here we're going to call V, but of course I'm not going to keep calling it V because there should be better notation than just V. So we write this as T gamma of TA is A, and then the vector V we're going to call gamma prime of T. Okay, so i.e. gamma prime of T is T gamma of T1. Okay. And so, you know, when you see the notation prime, you think derivative, right? And of course, that's what this is. So in coordinates, for M, okay, if T goes to x1 of T, xn of T is the local representative for gamma, then the local representative for gamma prime is T goes to, okay, so the local is, so what will gamma prime of T be? So gamma prime of T is a tangent vector at gamma of T to M. Okay, and so when I write the local representative for gamma prime, it's going to have two parts to it. It's going to have the gamma of T part, which I've already written down, and then it's going to have the tangent vector part. And the tangent vector part is just the derivative of the local representative of gamma, which is that, with respect to T. So, which is just what we showed last time. So the point is that this is x1 of T, xn of T, x dot 1 of T, x dot n of T. Okay. All right. And so gamma prime is what you might think of as being the tangent vector field along gamma. And I'll draw a picture attached to that. Okay, and the picture is this. Okay, so here's our curve gamma, like so. Okay, and the point is that at a point, let's say T here, which maps to gamma of T here, you're going to have a tangent vector attached to that point, which is gamma prime of T. Okay, so it's you know, just kind of like the velocity along the curve. Okay. All right, so there's two sort of important applications of the derivative of a mapping. You know, this one we're going to come back to every now and then. Okay. All right, so now we're going to go back to physics, and we're going to talk about rigid body velocities. Okay. All right, so the scenario here. So when we've talked, when we've been thinking about velocity in terms of manifolds, we had a curve and we took an equivalence causative curve to get a tangent vector, and the tangent vector you could think of as being the velocity at that point as you go around the curve, just like I drew in the picture just above. Okay. Now what we're going to do is we're going to look specifically at rigid bodies, and we're going to put a rigid body in motion. Okay, so consider a rigid body in motion. Okay, so what do I mean by that? I simply mean that I have a curve in SO3 cross R3, right? So I've done the stuff that we've talked about in the past when we talked about configuration manifolds. So I've chosen a spatial frame. I put a body frame in the body, and so when the body goes in motion, then that's going to get me a curve in SO3 cross R3, where SO3 cross R3 is kind of the free configuration space of the body. Okay. All right. So then. Okay, so well, we have a notion of velocity already, right? So which is sort of direct and straightforward, but turns out it's not the one we're going to use. We're going to use one that's much easier to work with and has a simple interpretation. Okay, so the problem, the challenging thing is the kind of rotational velocity. Okay, so the velocity which kind of corresponds to that part of the rigid body motion. And so notice that R is in SO3. Okay, and SO3 is an element of SO3 is a 3 by 3 matrix. So this sits inside, oops, R3 by 3 cross R3, right? Okay, and why did I take the time to point that out? Well, the point is that this curve really evolves in a quite simple manifold. It evolves in sort of a complicated subset of a simple manifold, namely SO3. But this itself is quite simple. And so when we talk about the velocity, we can just freely differentiate like we were in second year calculus, because this is just a Euclidean space. Okay, it's a 12-dimensional Euclidean space. Okay. And so you can write R dot of T, R dot of T. Okay, so this will be the tangent vector to this curve at time t. So it'll be a tangent vector at the point big R of t, little r of t. Okay, and so this will live in t, r of t, r of t, SO3 cross R3. Okay, and this itself, just by what I wrote here, and so you could you can easily just put t's in front of these things as well, and the inclusion still holds. Okay, so this is going to be a subset of t at r of t, r of t, R3 by 3 cross R3. Okay, and then again, the reason I'm kind of belaboring this point, and then because this is just a Euclidean space, the tangent space is just isomorphic to the Euclidean space itself, and so this is isomorphic to R3 by 3 cross R3. Okay. And so the reason I belabor this is that this is simple, right? This is the thing you just calculate it. You just kind of write down normal second year calculus time derivatives, right? But as I say, it turns out that's not the best way to represent rigid body velocities, and in particular, it's not the best way to represent the kind of rotational velocity. All right, and we're going to use different representations for the rotational velocity. Okay, so I'm going to define 4 different velocities. Two of them are going to be the same, and we'll talk a little bit about that. And 2 of them are going to be kind of translational velocities, and 2 of them are going to be angular velocities. Okay, so the body angular velocity is, and I use the symbol, GAC. I'm very sorry, what I'm going to have to do here, I always do this because I forget to define a symbol before I start writing down these definitions. So I'll do it down here. So define, first of all, let's denote by little SO3, okay? So that's little SO3. And if you're playing along with LaTeX, I hope you are, the correct font for this is MathFrac. Okay, but I'm unable to produce MathFrac well enough by hand, so I just write in a lowercase script font. Okay, and so what is this? This is the set of 3 by 3 skew symmetric matrices. Okay, so in other words, SO3 is A in R3 by 3, so that A transpose is minus A. Okay, then define a mapping. And I'm going to call this mapping hat. Okay, and this mapping goes from R3 into SO3. Okay, and what is this mapping? So this mapping takes a vector A1, A2, A3 in R3, and it maps it to a certain skew symmetric matrix. And the way that you assemble this matrix, specifically matters. And here's how you do it. So first of all, every skew symmetric matrix always has zeros on the diagonal. And so it's really, and then the upper diagonal terms determine the lower diagonal terms. And so it turns out that the thing you put here is right. Okay, so this is A3 and minus A3, and then 0, and then 0. And then here it's A minus A1 and A1, and then it's A2 and minus A2. Okay. So there's a very precise way of doing that. And the locations of the 3s and the 1s and the 2s, and also the minus signs, they matter. Okay. So this is the thing we call a hat. And another way of defining a hat is, so if I give you a vector in R3, then little a, and then I take its hat, and then I multiply that by a vector b. Okay, so now this product here is the product of a 3 by 3 matrix with a vector. Okay, and another way of defining the hat map is to say that this is A cross B, and this is the normal cross product in R3 that you're familiar with from vector calculus. Okay. All right, so that's the hat map because I need the hat map here. And so what's the inverse of the hat map? So the inverse of hat is upside down hat. And this now is a map from SO3 into R3. Okay. All right, so sorry, I should have given that first, but there's this construction. So we're going to be using this a lot. Okay, so the definition of body angular velocity relies on this hat map, and here's how I define it. So the symbol I use for the body angular velocity, I use a capital omega. Okay, and here's what you do. You go R transpose of T, R dot of T. Okay. All right, so now let's make sure we understand what we're doing here. This is a 3x3 matrix, and it's just the matrix of time derivatives of R. Okay, so that's a simple thing. This is also a 3x3 matrix, and it's the transpose of R. And remember that the transpose of R is also equal to the inverse of R because R is orthogonal. Okay, so the point is that the resulting thing here is a 3x3 matrix, and it turns out, and we're going to show that shortly, that it's a skew symmetric 3x3 matrix. And so what I need to do is I need to convert, because this is going to be a vector in R3, so I convert this 3x3 skew symmetric 3x3 matrix into a 3 vector by taking the inverse hat map. Okay. And then the spatial angular velocity is, okay, so it's a rather similar construction. And I write the symbol as little omega of T, and I take, just sort of reverse the symbols, R of T, R transpose of T, and then I take the inverse of the hat map. Okay, so those are there's two flavors of angular velocity that we can use, and I'll give you interpretations for how to think about what these mean, and we will use both. Okay, and the body translational velocity is V of T equals, and I'm just going to use R dot of T here. And I'm going to define the spatial one. I'm going to define it to be the same, although that's not true. Okay. So there's a correct way to define the body translational velocity and the spatial translational velocity. And neither of those correct ways is that it's R dot. Okay, so I'm doing something wrong here in a certain sense, but it's a little bit of a trip to see why it's wrong and what wrong even means. There's sort of a general framework in which you can build these kinds of definitions, and then natural definitions of body and spatial translational velocity pop out, and they're not R dot, it turns out. Okay, but I don't really care. This is the one we're going to use just because it's the easiest. Okay, so these are wrong. And I only want to say that in case you go and you take at some point a serious version of rigid body motion and you talk about these things, you will see in a decent mathematical robotics course, which this course is in some ways, but not in this way, I guess. You'll see a correct derivation of this. but it's not worth the trouble here. Okay. All right. So first of all, I need to make sure this definition actually makes sense, because in the definition of the angular velocities, I've checked them, taken the upside down hat, which is called check. And so in order for this to make sense, this thing and this thing have to be skew symmetric. So let's verify that that's the case. Okay. So this is easy. You kind of, just take the definition of R and differentiate it. Okay, so the definition of R is that R transpose of T, R of T is equal to the 3x3 identity matrix, right? That's the definition of O3, and so something in SO3 also satisfies that. Okay, then I differentiate and I get R dot transpose of T, R of T, plus, so let me maybe move it, the derivative of the identity will be 0, so I'll just move this immediately over to the other side. So I'm going to get minus R transpose of T, R dot of T, okay? And so that right there is capital omega. That's the body angular velocity, and so I need to show that well, so this thing is minus the body angular velocity, so I need to show that this is the body angular velocity. But you just use the fact that the transpose of a product is the swapped product of the transposes. Okay, so this is R transpose of T, R dot of T transpose, and this is well, here, let me finish writing it out. So this is R transpose of T, R dot of T, and so taking transposes on both sides, what I get is that omega of T, well, is equal to minus omega of T transpose, or the other way around. Okay. All right, and then similarly, for little omega, the only difference, of course, is that you change the order here. You do R transpose. Okay. All right, so these definitions make sense. All right, so okay, let's think if we can come up with a physical interpretation of what these angular velocities are. Okay. All right, so first, what you can, so among all rigid body motions, are those which are rotation about some axis. Okay, so what I mean by that is this, is that, so if you can see my, see me here. So here's an axis, here's my vector A, my wand. And so you can consider then rigid body motions, which are just rotations around A. Well, I guess the way I've drawn A, the rotations, if we're talking about positive rotations, are going to be like this, okay, by the right-hand rule. Okay, and so that's what I mean by a rotation about A. So mathematically, a rotation about A is given by, okay, so this is a neat formula. So, so if I have a rigid body and I have a vector A, what should capital R of T be in order for it to be a rotation about A? So it's given by R of T is equal to E to the A hat T, okay? And so this is the matrix exponential, which I suppose you're familiar with. If you're not, it doesn't matter, but I can write down a definition for what it's worth. Okay, there's the definition of the matrix exponential. It's just like the normal exponential. That doesn't actually tell you squat about the matrix exponential, but there's the definition. But it turns out that a rotation about an axis A is given by that. And if you want to kind of see why, what you can do is what should the rotation about a vector satisfy? Well, it should satisfy that if you apply that rotation to the vector itself, then it should leave the vector alone, right? Because it's rotating about that vector. And so you can check that, and you can use the definition to check this. You can check that R of T A is equal to A, for example. Okay, so it leaves the vector about which you're rotating fixed. Okay, so that's fact number one. Okay. Fact number two is that at a time t, any motion t goes to, and now I'm just interested in rotations, so I'm just going to be talking about the R of T. Okay, so about any rotating motion, T goes to R of T. At a time T, there exists an axis, and I write this axis as A sub T, okay, because the axis will generally change as the time changes, so that R of T and E to the A hat T, okay, so there's two, so I shouldn't use, no, yeah, T is fine, so that these things agree to first order. Actually, I think I want to not have that be the same T up there. So let me do it this way. So at any time T naught, okay, there exists an axis A T naught, so that R of T and A T naught T agree to first order. At T equals T naught. Okay, so what I mean by that is their velocities agree. Okay, and so what that means is, if I have an arbitrary motion, so my body, and remember I represent a body by a frame, okay, so my body is undergoing some kind of arbitrary motion or rotation, but if I fix a time t, then the velocity as I pass through that time, as I pass through the point at time t, there's going to be just a pure rotation about some axis whose velocity is equal to the velocity of the body at that point. Okay, so that's what I mean by agrees to first order. Okay, all right, and so then a hat t naught is equal to the spatial angular velocity at t naught. Okay. All right, so that gives you the interpretation of the spatial angular velocity. At any time t naught, the spatial angular velocity at time t naught is the axis about which the body is rotating at that instant. Okay, and the axis can change. Okay, and so I need hats here. Sorry. Okay, but that's how you interpret what the spatial angular velocity is. Then the body angular velocity it's probably just easiest to remove the hats here. Okay. Then the body angular velocity is omega of t, the spatial angular velocity, but in body coordinates. So let me sort of say that in the language that I've been using. So, but in the body frame. Okay, so little omega is, spatial. So little omega is in the spatial frame, and so if I imagine, so I have a fixed spatial frame. Okay, and then the body is over here kind of rotating, and so at each time t, I'm going to have an axis about which the body rotates, which I represent in the spatial frame, and then if I view that axis from the body frame, that's what the body angular velocity is. Okay. All right. Okay, and so that's how you can interpret what these angular velocities are. So obviously, v of t is the velocity of the body origin, because v of t is just little r dot, and little r is the vector from the spatial origin to the body origin, and so v is the velocity of the body origin measured in the spatial frame. Okay. All right. So corresponding to all of this is there's ways that you can assemble these velocities into a pair of maps, okay, when I call these iota body and iota spatial. Okay, so really, all these things is it's a way of taking an interconnected mechanical system and sort of assembling all of its velocities into one big long thing, and so that's what we're going to do next time. Okay, it's nothing more than just doing what we did today, constructing these four four velocities here, and sort of just, putting them in components of some gigantic mapping. Okay. All right. So I will stop the recording